From the Big Bang to dark energy, knowledge of the cosmos is sped up in the past century, but questions linger. The most fantastic story of all time, especially the early chapters, written in the history during the first 200 to 300 million years of the universe's 13.8 billion year existence, still isn't fully understood, and that puzzles scientists. But now, abiding by the rules of space and time, the further away we look in space, the further away we look in time as well, we are ready to lift the occult veil on the cosmos thanks to the James Webb Space Telescope. Well known as an engineering marvel built by the world's leading scientists and engineers, the James Webb Space Telescope, or JWST, has given us a more intricate understanding of galaxies, stars, and the atmospheres of planets outside our solar system than ever before. Every new image is a new discovery, empowering scientists around the globe to ask and answer questions they once could never dream of. And in a remarkable find, the JWST just captured the first images of an ancient supernova that could help solve one of the universe's biggest inconsistencies. Join us today as we dig deep into how James Webb's first supernova discovery could quite simply save the universe. One of the great theoretical developments of modern astrophysics and cosmology comes straight out of general relativity and just one simple realization: that the universe, on the largest cosmic scales, is both 1. Uniform, or the same at all locations, and 2. Isotropic, or the same in all directions. As soon as you make those two assumptions, the Einstein field equations, the equations that govern how the curvature and expansion of space-time and the matter and energy contents of the universe are related to each other, reduce to very simple, straightforward rules. Those rules teach us that the universe cannot be static, but rather must be either expanding or contracting, and that measuring the universe itself is the only way to determine which scenario is true. Furthermore, measuring how the expansion rate has changed over time teaches you what's present in our universe and in what relative amounts. Similarly, if you know how the universe expands at any one point in its history, and also what all the different forms of matter and energy are present in the universe, you can determine how it has expanded and how it will expand at any point in the past or future. It's an incredibly powerful piece of theoretical weaponry. But to get that weapon, we just need one strategy, which is as straightforward as it gets. First, you measure the distances to the astronomical objects that you can take those measurements of directly. Then, you can try to find correlations between intrinsic properties of those objects that you can easily measure, like how long a variable star takes to brighten to its maximum, fade to a minimum, and then re-brighten to its maximum again, as well as something that's more difficult to measure, like how intrinsically bright that object is. Next, you find those same types of objects farther away, like in galaxies other than the Milky Way, and you use the measurements you can make, along with your knowledge of how observed brightness and distances are related to one another, to determine the distance to those galaxies. Afterward, you measure extremely bright events or properties of those galaxies, like how their surface brightnesses fluctuate, how the stars within them revolve around the galactic center, or how certain bright events, like supernovae, occur within them. And finally, you look for those same signatures in faraway galaxies, again hoping to use the nearby objects to anchor your more distant observations, providing you with a way to measure the distances to very faraway objects, while also being able to measure how much the universe has cumulatively expanded over the time when the light was emitted to when it arrives at your eyes. We call this method the cosmic distance ladder, since each rung on the ladder is straightforward, but moving to the next one farther out relies on the sturdiness of the rung beneath it. For a long time, an enormous number of rungs were required to go out to the farthest distances in the universe, and it was exceedingly difficult to reach distances of 1 billion light-years or more. With recent advances in not only telescope technology and observational techniques, but also in understanding the uncertainty surrounding the individual measurements, we've been able to completely revolutionize distance ladder science. About 40 years ago, there were perhaps 7 or 8 rungs on the distance ladder. They brought you out to distances of under 1 billion light-years, and the uncertainty in the rate of expansion of the universe was about a factor of 2, between 50 and 100 kilometers per second per megaparsec. 2 decades ago, the results of the Hubble Space Telescope Key project were released, and the number of necessary rungs were brought down to about 5. Distances brought you out to a few billion light-years, and the uncertainty in the expansion rate reduced to a much smaller value, between 65 and 79 kilometers per second per megaparsec. However, today there are only 3 rungs needed on the distance ladder, as we can go directly from measuring the parallax of variable stars, such as Cepheids, which tells us the distance to them, to measuring those same classes of stars in nearby galaxies, where those galaxies have contained at least one Type 1a supernova, to measuring Type 1a supernovae out to the farthest reaches of the distant universe, where we can see them, up to tens of billions of light-years away. Through a Herculean set of efforts from many observational astronomers, all the uncertainties that had long plagued those differing sets of observations have been reduced below the level of less than 1%. All told, the expansion rate is now robustly determined to be about 73 to 74 kilometers per second per megaparsec, with an uncertainty of merely plus or minus 1 kilometers per second per megaparsec atop that. For the first time in history, the cosmic distance ladder, from the present day looking back more than 10 billion years in cosmic history, has given us the expansion rate of the universe to a very high precision. However, note that there is a completely different method we can use to independently solve the exact same puzzle, the early relic method. When the hot Big Bang begins, the universe is almost, but not quite perfectly, uniform. While the temperatures and densities are initially the same everywhere, in all locations and in all directions, to about 99.997% precision, by the way, there are those tiny 0.003% imperfections in both. Theoretically, they were generated by cosmic inflation, which predicts their spectrum very accurately. Dynamically, the regions of slightly higher than average density will preferentially attract more and more matter into them, leading to the gravitational growth of structure and, eventually, the entire cosmic web. However, the presence of 2 types of matter, normal and dark matter, as well as radiation, which collides with normal matter but not with dark matter, causes what we call acoustic peaks, meaning that the matter tries to collapse but rebounds, creating a series of peaks and valleys in the densities we observe on various scales. These peaks and valleys show up in 2 places at very early times. They appear in the leftover glow from the Big Bang, the cosmic microwave background, when we look at the temperature fluctuations, or the departures from the average 2.275 Kelvin temperature in the radiation leftover from the Big Bang, we find that they are roughly 0.003% of that magnitude on large cosmic scales, rising to a maximum of about greater than 1 degree or smaller angular scales. They then rise, fall, rise again, etc., for a total of about 7 acoustic peaks. The size and scale of these peaks, calculable from when the universe was only 380,000 years old, then come to us at present dependent solely on how the universe is expanded from the time that light was emitted, all the way back then to the present day, 13.8 billion years later. They show up in the large-scale clustering of galaxies, where that original 1 degree scale peak has now expanded to correspond to a distance of around 500 million light-years. Whenever you have a galaxy, you're somewhat more likely to find another galaxy 500 light-years away than you are to find one either 400 or 600 million light-years away, evidence of that very same imprint. By tracing how that distance scale has changed as the universe has expanded, by using a standard ruler instead of a standard candle, we can determine how the universe has expanded over its history. The issue with this is that, whether you use the cosmic microwave background or the features we see in the large-scale structure of the universe, you get a consistent answer, 67 kilometers per second per megaparsec, with an uncertainty of only plus or minus 0.7 kilometers per second per megaparsec, or about 1%. That's the problem. That's the puzzle. We call the conundrum the Hubble tension, after astronomer Edwin Hubble. In 1929, Edwin Hubble observed that the farther a galaxy is from us, the faster it recedes, an observation that helped pave the way toward our current notion of the universe, starting with a Big Bang and expanding ever since. The Hubble tension comes from attempts to measure or predict the universe's current rate of expansion. Currently, we have two fundamentally different ways of how the universe has expanded over its history. Each is entirely self-consistent. All distance ladder methods and all early relic methods give the same answers as one another, and those answers fundamentally disagree between those two models. If there truly are no major errors that either sets of teams are making, then something simply doesn't add up about our understanding of how the universe has expanded. From 380,000 years after the Big Bang to the present day, 13.8 billion years later, we know how much the universe has expanded by, the ingredients of the various types of energy that exist in the universe, the rules that govern the universe, like general relativity. Unless there's a mistake somewhere that we haven't identified, it's extremely difficult to concoct an explanation that reconciles these two classes of measurements without invoking some sort of new exotic physics. As such, this problem has confused scientists for decades. The scientific community even call the Hubble tension one of the greatest puzzles in modern astronomy. Evidence of this conundrum has been accumulating for years, causing some researchers to call it a looming crisis in cosmology. But now, a twist is coming, and that's thanks to the spectacular appearance of the James Webb Space Telescope. According to scientists, James Webb's first triple-image supernova could help us finally solve a long-standing inconsistency about the universe that has threatened to unravel our understanding of the cosmos. The Type 1a supernova, named supernova H0PE, or HOPE for short, was first discovered lurking the photographs captured by James Webb in March. In these images, the exploding star can be seen as an arc of orange light with three bright points that surround part of the galaxy cluster PLCK G165.7 plus 67.0, or G165 for short, which is around 4.5 billion light-years from Earth. The light arc is the result of gravitational lensing, an effect caused when light from a distant object, such as a supernova, passes through space-time that has been warped by the gravity of a massive foreground object, like a large galaxy, that is positioned directly between the distant object and the observer. This also magnifies the distant object, making it easier for researchers to analyze. The three bright spots in the arc around G165 make it seem like there are three separate light sources being visually manipulated, or lensed by the foreground galaxy. But, in reality, the supernova, which is located around 16 billion light-years from us, has been duplicated twice by the lensing effect. In a new article published on BigThink.com on September the 20th, astrophysicist and science communicator Ethan Siegel, who was not only involved in the study, wrote that supernova HOPE could help solve the long-standing inconsistency about the expansion of the universe, the Hubble tension. Supernova HOPE could help solve the Hubble tension because it is a Type 1a supernova, which astronomers refer to as a standard candle, an incredibly reliable reference point from which we can measure the universe's expansion, Siegel wrote. Type 1a supernovas involve a white dwarf star stealing matter from a binary partner star before reaching critical mass and exploding. These bright explosions have all near equal initial luminosity and dim over time at the same rate. By comparing these standard candles at various distances from Earth, scientists can work out exactly how fast they are moving away from us and can then deduce the expansion rate of the universe. Supernova Hope is a particularly important standard candle because it is the second most distant star 1A supernova ever detected, Siegel wrote. The strong gravitational lensing and duplication in the new images also gives researchers more information to work with than normal, he added. The idea of using duplicated supernovae to tackle the problem of Hubble tension is not new. In May, scientists used data from a reappearing quadruple-lensed supernova named Refsdal to calculate a new value for the Hubble constant. Although this still differed from the value calculated using the cosmic microwave background, the distance between the two was reduced, suggesting that they could one day match up. It is currently unclear whether supernovae Hope can be used to calculate an even more reliable value for the Hubble constant. But researchers are confident that if James Webb's keen eye can continue to pick out more distant standard candles, the problem of the Hubble tension may finally be solved. While Webb's new observations could help solve one of the universe's biggest inconsistencies, astronomers have also just figured out one of Webb's first puzzles. When the JWST began science operations in the summer of 2022, its deep observations of the universe quickly began turning up high redshift galaxies. These are galaxies that seem to have existed earlier in the universe than astronomers had ever seen before. In fact, the galaxies which were seen as they were when the universe was less than 400 million years old appeared more luminous than what the standard model of cosmology predicts for the era. This led to claims that the standard model, which depicts galaxies starting off small and then growing hierarchically through mergers driven by filaments and halos of dark matter in the cosmic web, must be wrong. As Claude-André Faucher-Giguère of Northwestern University said in a statement, the discovery of these galaxies was a big surprise because they were substantially brighter than anticipated. Typically, a galaxy is bright because it's big, but since these galaxies formed at cosmic dawn, not enough time has passed since the Big Bang. How could these massive galaxies assemble so quickly, he asked. The conundrum has flummoxed astronomers since that time. But now, we have an answer. Just a few days ago, scientists led by Guokao Sun at the Center for Interdisciplinary Exploration and Research in Astrophysics and a postdoctoral fellow at Northwestern University have discovered new evidence that a process called bursty star formation could naturally explain the existence of the galaxies without invoking any new physics. Bursty star formation occurs when galaxies experience a baby boom of stars that is unusually intense, making these objects extremely bright even at great distances. The brightness of a galaxy normally correlates to its mass, but bursty star formation might make these ancient galaxies appear much more massive than they actually are, a finding that could solve this perplexing mystery. Sun and his colleagues used sophisticated simulations to demonstrate that bursty star formation naturally explained the abundance of bright galaxy at cosmic dawn, according to a study published on Tuesday in the Astrophysical Journal Letters. Now we have actual data. We can go back to simulations produced before the launch of the James Webb to draw an apples-to-apples comparison and see how they agree. It turns out that our simulations agree with the observations pretty well, Sun said, and we can show that burstiness actually plays an important role, because if we remove the burstiness from our simulations, we won't be able to match the observations, Sun said. Scientists have seen traces of these bright galaxies at cosmic dawn for many years, but James Webb, which is the most powerful telescope ever launched to space, threw them into sharper focus and revealed that they are common at cosmic dawn. The telescope's observations have sparked a huge debate among astronomers and cosmologists about the unknown mechanisms that could fuel the formation of such apparent massive objects over a short time scale in which they really shouldn't exist. Sun and his colleagues are not the first to suggest that bursty star formation could be a critical piece of this puzzle, and the team noted that many other factors might play a role in the brightness of the galaxies. However, the new study's state-of-the-art simulations, which were developed by a project called Feedback of Relativistic Environments, or FIRE, show that episodes of bursty star formation can dramatically brighten galaxies in ways that fit well with the James Webb's discoveries. According to Sun, the role played by bursty star formation is something we're not so surprised about because our simulations predict bursty star formation in these early epochs. What we didn't entirely expand is the absolute extent to which these predictions and observations agree. We know it's important, but we don't know if that's the full story, he said. There are still many moving parts and things that need to be ironed out, and those will be natural steps for us to look forward to in the future. To that end, Sun and his colleagues plan to continue running their FIRE simulations to pinpoint how much bursty star formation contributes to the brightness of these early galaxies, and to investigate other mechanisms that might also be in the mix. Bursty star formation has been observed in many galaxies across the universe's lifespan, but the underlying dynamics of the brilliant episodes is still poorly understood, which raises other open questions that the team hopes to pursue. For now, though, Sun said that the results suggest that the bright galaxies do not necessarily pose a challenge to the Standard Model, or Lambda Cold Dark Matter model. As Sun concluded, it's too early to say anything conclusive about the Lambda Cold Dark Matter model, especially if we want to break it. The astrophysics of those very early galaxies are very much like the tip of the iceberg that we see, but in order to say something about the big picture, we need to be super careful or cautious about any potential pitfalls or unaccounted physics that might bias our assessment and analysis. As a piece of interesting news, the Hubble Space Telescope recently observed something strange. An extremely bright, extremely fast flash of light that popped up in the middle of nowhere. Technically known as a luminous fast blue optical transient, or LFBOT, the odd thing about this rare event was that it occurs outside of a galaxy. These flashes have been observed only a few times since they were discovered in 2018, and this particular event was named the Finch. Hubble was used to track the flash's origin point, which was in between two galaxies, 50,000 light-years away from a larger spiral galaxy and around 15,000 light-years away from a smaller galaxy. This has astronomers puzzled, as these events were thought to issue from inside galaxies where stars are forming, but this event happened far away from any star-forming region. The Hubble observations were really the crucial thing. They made us realize that this was unusual compared to the other ones like that, because without the Hubble data, we would not have known, said lead researcher Ashley Crimes in a statement. The flash was also discovered using other instruments, like the ground-based Gemini South Observatory, which found that the temperature of the Finch was an incredible 20,000 degrees Celsius, approximately 36,000 degrees Fahrenheit. These flashes brighten and dim in just a few days, compared to other brief astronomical events like supernovas, which tend to brighten and dim over a period of months. Scientists thought that the LFBOTs might be created by a particular and rare type of supernova that happens to very large and short-lived stars. As these stars don't last for long, they tend to be found close to stellar nurseries where they are born. But this new flash challenges that concept. The more we learn about LFBOTs, the more they surprise us, says Crimes. We've now shown that Aleph Bots can occur a long way from the center of the nearest galaxy, and the location of the Finch is not what we expect for any kind of supernova, she said. It could be that the flashes are not in fact caused by supernovas, but are instead caused by stars being ripped apart by black holes. Or it could be that a fast-moving star was passing between the two galaxies and exploded during its journey. As the events are so rare, it's hard to tell at this stage of research. The discovery poses many more questions than it answers, says Crimes. More work is needed to figure out which of the many possible explanations is the right one, she concluded. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. And as always, thanks for watching, and we'll see you next time.